let's discuss the warm-up and maybe a solution to the bonus problem for those who have gotten it, and then just keep in mind that, like I said, I'd like to do some cleanup today. So if you have some questions, maybe you can start thinking about the questions from really any of the past couple homeworks. Like I know a couple of you had questions for the end of homework 5, the book homework. You had like some questions on the end where you were trying to like restrict the function to be in certain quadrants using, what would the restriction on C be? Some of you had some questions around that. Some of you had some questions on homework 7, which was lines. I'd be happy to answer some of those. I know there's some questions from last night as well. There's an example we didn't get to yesterday. I could do that for you. There are like a host of different options available to us today. I think we'll have plenty of things to do with our 45 minutes, that's for sure. I'm not worried. So let's start with this, and then we'll go to one of those things. But I just want to tell you what we're doing, so like already you can like ready a question for me if you have one. First of all, the first thing to say is like, do you agree with what George did? Do you like this? I know there's still some people out there who don't know how to find the intersection between the two lines. So please try to become someone who is able to do that. Okay. Remember, like I said a second ago, you want to swap t for s. And the reason there, like, let's think about what that would mean, in fact. We're saying that both of these lines contain this point at for some particular parameter. But it's not true that the parameter is the same for both lines. So if you're thinking about parametric equations here as being space curves, right, for some projectile motion of some kind or whatever, like, then the way you might visualize this is like two flies that are flying through the room on linear paths in three-dimensional space. And they're like contrails, if flies had contrails, cross at this point. But did the flies actually collide? No. They missed each other by like a second, right? One passed the point at t equals 2, and a second later at t equals 3, the other one passed that exact same point. So you understand, like, if we were to graph these two lines in space, they would intersect at this point. True. But if you were trying to think about, like, the t and the s piece, then it's not the same time, quote unquote. I mean, we don't have to think about times, but I just want to make sure you understand the difference there. And then, does someone want to discuss? I don't know. I know there was some discussion about this piece up here, up in this area. Does anyone else have a discussion elsewhere? I don't know whether about that second piece. Could you come up with an equation of a line now passing through the intersection of the lines we just calculated, that is through the point 2, negative 1, 2, and, extra requirement, perpendicular to both of those original two lines? Even if you didn't do it, can you come up with a way to do that? Yeah, go ahead. Okay, so the general idea is, do you agree with this up here, up at the top? These are the parametric equations for the lines. He said I'd rather see them this way. And then he's saying, hey, if there's an intersection, then it must be true that that's the case, right? That for some s and for some t value, the x values are the same. And for some s and t value, the y values are the same. So ignoring the last one, for now at least, can you solve this system of equations? That's what it is. Negative 4 plus 2t equals s. And 5 minus 2t equals negative 7 plus 3s. That's a system of two equations, linear system of two equations and two unknowns. Solve it using whatever method you like. Looks like he did that here and found s equals 2 and t equals 3. The only other thing you should check then is that, if you did your algebra right, then that should generate for us an x and a y that are the same from both sets of equations. But then the thing we haven't looked at yet is the z. So we should just verify that, in fact, now I told you that it would work because I said the way I phrased the question. But we haven't done these, so it should work though for z2, hopefully. But I have also asked you the question the following way. I think on the homework I asked you, do they intersect? Question mark. And if so, please tell me what the intersection is. So what does it feel like when this fails? Like if I say if they don't intersect? Yeah. Yeah, the z's don't equal when you try this. Like, so don't be a cavalier and just be like, oh, this always works. It's possible that you get through this whole system of equations. You get s equals 2 and t equals 3. Yay! and you write this down, but you need to check that for x, y, and z, you're getting for all three of those, you're getting the same point from both lines when you plug in the t and the x respectively. Okay. So anyway, okay. So sorry, back to this now. Why are you bringing the cross product into this?
The cross product always yields orthogonal.
Oh, look at all this technical language. You use the word cross product and orthogonal in the same sentence. That's awesome. Yeah, totally. Yes, totally. The cross product maybe does need to enter in here. Of what? What are you talking about?
Of the value of each of them.
Yeah.
It's the direction vector.
Right. Cross the direction vectors, -2, -2, 1, cross 1, 3, 4, and you'll get something. You have it? It's right this time?
Yeah.
Okay. -11.
-7.
-7. 8. Okay. So then, once you have that, now you have a direction vector for your new line.
And then don't you use
And you have a position vector right here, and you can just write it down. It's x, y, z. By the way, there's more work to be shown here. We just stated over the details, right? What is that? 2, -1, 2, plus t times this, -11, -7, 8. Now, curiously, by the way, I think this is completely coincidental by me. I didn't really mean this to happen, but is there anything interesting about the original two lines? Yeah, the two original lines are actually perpendicular, which means all three of these are mutually perpendicular, which means they kind of form a new like a new set of axes in space, don't they? Yeah, that's like a really interesting idea that you'll explore more in linear algebra too. This idea of like having another, it's called an orthonormal basis for a coordinate system. Normal just means normal to each other, or perpendicular. Anyway, there's lots to be explored here for sure. And this is not the only interesting question I could ask. I mean, there's so many interesting questions we could ask in 3 dimensions, distance between points and lines and all sorts of things. Yeah. Yeah, it should be true that the direction vector we just got is the dot product of any of them is 0. Right. Yeah. Yeah. And it's coincidentally like also the dot product of these two. But yeah, the dot product of any pairwise should be 0 here. That's crazy, right? Special. It's fascinating. Life-changing. Okay. This stuff should make you like really think and really delight in the beauty of mathematics. Okay. Are we ready to talk about something else now? What? Yeah.
Okay, so on the where it asks someone in a baseball
Yeah. Hey guys.
X to minus y, how do you do that when you plug in 2 find out add a
So let me just make sure we're straight on this. We're like clearing the wall, and the way we did that yesterday was we said what x. They give you like the one we did in class was like the wall was 400 feet away, and so we first figured out when x would be 400. We found that time, t, and then once we found the time at which x reaches 400, we plugged that into y, and we found the height, and then we asked, okay, is that height y greater than or less than whatever the height of the wall was? And I think you had a problem. We did that kind of problem in class yesterday. It was, yay, it cleared the wall by a little bit. And then there was some like that on the homework too. Yeah. Did they all go over the wall on the homework?
No, only one of them went over with extra help.
Okay. Oh yeah, with wind or something. Here's the one from yesterday. I thought we'd put this in the calculator here just for fun. We didn't actually watch it yesterday, which made me sad. Right? We didn't actually watch it. So I want to watch this with you. I think it's pretty exhilarating. We already know the answer, that it goes over the wall, but I think I have this right. It's 125 cosine of 35. Okay, fine. This is the one we did in class yesterday at the end of our lesson yesterday. We were doing what?
You taught how to do that.
Well, was that the life-changing moment right there? Why is this so enormous? Why is this gigantic? Why is this so big?
Try the thing in the top right corner of the calculator.
What's wrong with this thing?
Oh, because you can't reach the zero.
I know, I can't reach the thing I need.
Wait, hold on. Let me get out the wood.
Alright, I guess, can I reach it now? I think I can now. Alright, here we go.
Hey, oh, this question. Yeah.
This is the one we did in class yesterday. Plus 125. Oh, wait, hold up. Oh, wait. Wait, where does it go? Plus. There we go. That's going to change your life, isn't it? Alright. Plus 4. Alright, so I think that's what we did. Plus 4.
Wait, hold on. Isn't that not? Oh, no, you took it.
Alright, and then I want the ball. Okay, and then I want a window that's like, how about 0 to 6? And then I want a t-step of 0.1 maybe. 0.1. 0.1. And we want to go from like 0 to 450 maybe, because that's where the wall is, 400, right? And 0 to 100, okay. All right, so if we watch, there goes the ball, right? Projectile motion, it's beautiful. Yay, all right. Now, what would be really exciting is if we could make the wall too. So let's do that. The wall is at 400 feet in X, and Y is like a line, so let's like have it go from 25 feet, which is the height of the wall, and then like, I don't know, what will this do? It'll just be 25, and then it'll like go down from there. So that'll be fun. Wait for it. Oh, it didn't graph my line because it already graphed, or my problem. All right, this time for real. Sorry, it's not being responsive. Come on now, come on now. It's so exciting. We could do this.
Chase, what was that magic thing that you did? Because I didn't see it. Everybody was yelling.
I want to make this wall just a little bit faster. That'll do. All right. This time we'll see the path too afterward. Maybe it was hard to see, so. All right. That's pretty exciting, right? All right. Now keep in mind, we did that. We did all that algebraically, which is probably still the better way to do it. But I just thought it'd be fun to see too. Okay. Yeah. All right. Listen up, guys. Isabel, you have another question, or you want to? One was from last night. Which one?
It's like the wind is going 5 miles per hour horizontally.
Yeah, so I
5
think.
feet per second horizontally, and how does that affect the ball?
So I think the only thing that affects if it's horizontal is the velocity vector. The velocity vector is we're adding 5 to the x velocity, right?
So is that I assume that it's like horizontally, but it's
I think they must have said a horizontal wind, right?
so would that be like parallel or is the horizontal purpose?
Is that good enough to say? Just add to the x velocity. 5. I think is what that was. I don't have it in front of me yet. Yeah, it's like this really well-behaved wind that only acts in the direction of the x-axis. Yeah, let me find it too here. Make sure I'm talking to you in the right way. 45. This is 45. So yeah, the y, I left my parametric equation for y unchanged. It's still like negative 16 t squared plus 120 sine 30 t plus 4. And then my epsilon was just 120 cosine 30 degrees plus 5, all of that times t. Is that okay? Does that make sense?
Wait, so what was the answer?
Yes, it clears with that extra little wind there. Yeah.
Wait, so the equation?
It's 120 cosine 30 degrees plus 5, all of that times t. Right. So the
wait, why wouldn't it be 120 whatever t plus 5? Like just add velocity.
So the velocity is increased by 5, right? And there's nothing that slows it down apparently in the x direction. So
The problem that I had is that I just added 5 to the
okay.
velocity.
Let me. Are we good on? Are we good on the Ferris wheel too? A couple people asked about that. Number 51. Do you want to do that? Talk about the Ferris wheel.
Yeah, mine looked kind of like a space machine that propels you to your death when I tried to craft it.
Okay.
Like make a pyramid and a turn with a leg
and then you die.
Let's see. Where do I have it here?
There was a point in time where I was trying to figure out if I could look up
I had it.
Let's make sure we're that could have been so crazy that I just saw what it would not.
All right. Pay attention. Pay attention. Pay attention. All right. We've got the coordinates cosine of t, comma sine of t, which generates if t is a number like I don't know, what's t? T equals whatever. What does that generate if you have cosine t, sine t? Yeah, let's watch that thing go here. This needs to get out of my way. That is. Whoa. Slow down. Okay. I can't really see that, so I'm gonna go like this. I want to see it. There it is. Okay. And let me. This calculator is really killing my style. Okay. There we go. Can you see that now? Okay. Are we having fun yet? Okay. What if we change this to be what is it we want in this problem? What do we want the Ferris wheel to have a radius of?
35.
The radius is 35? The radius is 35? Okay, we can do that. I mean, it's not a problem. There it is. Radius is 35. Now let's send it around again just because it's fun. Okay. And now, wait, hold up. There's more. It's also moved up a ways, isn't it? We also want to move y up by how much? Where's the center?
15.
Yeah, it's not given. It says 15 to the bottom, so but then plus 35 is 50. All right.
Would A be negative t because it starts at the bottom?
Wait, I'm busy, Maddie. Okay.
Sorry.
All right. It's working really well. It's working really well with one exception. Actually, it looks like the Ferris wheel that we're looking for, right? It's definitely got a radius of 35. Center is 50 feet off the ground, but it's not going as fast or as whatever we're supposed to make it go at, right? Like it's supposed to go the right speed. So we need to mess with how fast it goes. Let's say you want to make it like. Say you want to make it so that it goes really slow. Let's do that first. Like if you did this, let's wait for it. That would be one way. Let's watch. Notice by the way that like when you put 1/10 in 110t, it looks the same. The same graph is produced in the end, isn't it? It's still the same exact circle, regardless of what I put in here for this value, right? So it still charts the same circle. It's just going at different speeds. Okay. So we need to adjust this though, so that it goes. What's the part of the problem? So it makes one revolution every 12 seconds. So what would be a good thing to put in there? Jeremy, you look excited. Go.
So you can make circles, but is there a way to make a spiral?
Yeah. Well, let's do this first, and then we'll do spirals.
No,
It's pi over 6?
power. Yeah.
Why is it pi over 6? Because if you plug t equals 0 in, you get, if t is 0, we are here. Agreed? And if t is 12, where are we?
Same place.
Same place, right? So, right? At 12 seconds, we're back home. 0, 12, and at 6 seconds, we should be over here, right? All right, let's do it again here. It's so fun. Keep going around and around. I think we did it, right? So the parametric model is what I have up here. It's 35. Uh, 35. Here's the parametric model that is required for number 51 in the homework. 35 cosine of pi over 6 times t. 35 sine of pi over 6 times t plus 50, right? Now, I will say, the way we just developed that model was fun, wasn't it? Wasn't that fun? Okay. But you have done this before. The y-coordinate, this piece I've just highlighted, is a thing you've done before, right? In fact, let's just graph it here. Right? Do you remember this back in the day? All we did was model the height. Do you remember that? And that was just the height being modeled over time. So that makes sense, right? So at 0, I'm going to come up here and highlight it. At 0 seconds, you're here is your height, and at 12 seconds, apparently this is 12 seconds, is right here. Sorry, where is it? Yeah, here. It's 12 seconds. So that's what was happening. So then, at that point in our lives, we were only modeling the y value. You give me a time, I give you the height. But right now, we're modeling both things, right? You give me the time, I tell you the height. I also tell you the position, like what the distance your shadow is away from the center line on the ground, right? Like, does that make sense? So this is cool. You're modeling both. And you really have 3 variables happening, right? You give me a time and output. Outputted are 2 variables. So, is that exciting or what? Okay. Anything else you wanted to do in here? Was that fun? Okay. Jeremy wanted to do a spiral. Can someone tell me how to make a spiral? I love myself some cosine t sine t. I like that. I love that. What can I How do we make a spiral? How do we make a spiral? Yeah, we need the radius to be increasing. So how about this? I don't know the Cartesian coordinates for that, so we'll just go with it.
Oh, you could make it. Wait, so you would make, if you made it 1/2 t sine t, I guess it would be better, right? You can make it orderly part.
Right? All right, are we having fun yet? Okay. You do what you like. I mean, you do you. You know what I'm saying? Okay. All right. Anything else you want to do there? Let's, what do I want to do next? You want to talk about there's one example we didn't do yesterday. We could do is the capture the flag problem, which is fun. We could also do something from homework 5. That those problems at the end I was talking about where we're restricting t. Would you like to talk about that? I know that there were some, or we can do some of the line stuff. Whatever whatever you want to do. The lines worksheet was fun too. Let's talk. Let's do. So, are we all able to be on the same page right now? I'm looking at homework 5 because no one else is chiming in here. If you have something you want to do, then let's do it. But maybe this is a benefit to us. Homework 5 at the very end, 33, 34, 35, 36. Those 3 problems are interesting. So I thought to myself, let's look at those. I think they're fun. Let's do them. Okay. So let me make sure I get this right. There are, because I didn't write this down. I think they're giving you x and y, some parametric equations, and x is 2 minus absolute value of t. Is that x?
Yeah.
I have to think about it here. Oops. 2 minus absolute value of t, and t minus 0.5. Am I right or am I right?
You're right.
Okay. And then they ask you for each question, respectively, how would we restrict t in order for the coordinates we get to always be in the first quadrant? So let's start with that one. How do we do that? If we want to restrict to quadrant 1, then we require that what be true? What's true about x and y coordinates in quadrant 1? They're positive. Both are positive. So that is, we want 2 minus absolute value of t to be greater than 0. And we want t minus 0.5 to be greater than 0. So let's do this. So what does that mean? 2 is greater than absolute value of t, and over here t is greater than 0.5. So you could just kind of think about it, or you could like apply some rules from algebra that you might have known. This in particular, let's forget about that guy over there for a second. What does this imply? What does it mean for t to be, maybe we want to write it that way. T is less than, absolute value of t is less than 2. What does that mean? T is what? Between negative and positive 2, correct? And we also still have this requirement, and remember the word here is and. Okay, so you could do this with like a number line and shade the number line and kind of think about like Algebra 1 style, right? Or we could just kind of do it in our head. What is the set of values for which t is greater than 0.5 and also inside this interval? Well, it's like the intersection. And means like intersections, right? So I think, are we good with saying this? Okay, therefore, if t is in between this interval, we'll definitely have this thing being positive. That is y will be positive. Yay. We'll also have us inside this interval, which means x is going to be positive. All right, so that answers the first question. I think that might have been 33. Okay, what about quadrant 2? What's true about x and y coordinates in quadrant 2? Yeah, x this time, x is less than 0, and y is greater than 0. I guess that's all for today. We were having too much fun. That's how it works. Okay. Our t parameter was a little bit spicier than usual. Okay. Like I said, there is no official homework this weekend, but it would be a great idea to use 3 days on your project. You know what I'm saying? Take it easy, guys. And happy Valentine's Day.